Again, my name's Peter Donovan. I'm with a nonprofit organization called the Soil Carbon Coalition. I'm out of Enterprise, Oregon, and we do a lot of soil sampling around the country. In 2010, we started the Soil Carbon Challenge, which is a measurement monitoring project, not a research project in the traditional sense, but a monitoring one. And the objective of that is to try and show what's possible under the best, most innovative management. And we've worked mainly with graziers on this. And I'll be talking about that a little bit later in the presentation. What I'd like to start with is kind of a big picture. A lot of people have a lot of different opinions or perceptions of the carbon cycle, depending on their incentives. If they want to see a carbon market, or if they don't want to see a carbon market, or whatever it is. There's a lot of different perceptions and incentives about the soil carbon question. And we're not taking any particular position as an organization. We're not advocates for a carbon trading market or anything like that. What we'd like to do is to help people understand the importance of good carbon cycling, slowing down the carbon cycle, if you will, and that it's possible to measure it, and that it's possible to recognize some outstanding results. In the talks I give, I notice there's a lot of demand for answers, and I'm more of a question guy. And I know that's frustrating for a lot of people, so I just want to bear with me, just ask you to bear with me on this. And it's not a technical problem, it's a human issue, as I think my first slide is trying to get at. We have a lot of problems, and I like to ask, what are the incentives for dividing an opportunity into multiple competing problems? And we spend a lot of money and effort protecting turf in trying to solve or offer solutions to these problems. So just keep in mind that question. What are the incentives for dividing an opportunity, and I'll talk about the opportunity as we go along here, into multiple competing and probably insoluble problems as individual problems. These are probably insoluble. As I mentioned, I get asked a lot of questions, being kind of a soil carbon focused person. And one of the most typical common questions that I get asked is, what species can we plant to increase soil carbon? And I used to hate that question because I'd short circuit, there would be smoke coming out of my ears, but I finally figured out the answer to that question. And this is the species that we need to plant. Because that little girl in North Dakota, she's now 7 or 8 years old, and she follows her dad around everywhere, figuring out cover crop mixes and grazing strategies and all that stuff like that. And so human management, committed, imaginative, creative human management is what we need to build or grow soil carbon. And people we're always focused on what's possible. What can we do? What do we have the power to do? So I want to talk a little bit about power today, because I think it's a big context on everything that happens. And on Earth, almost all power comes from the sun. And I'm talking literally power. We have some residual heat from the Earth's center that's caused by probably residual heat of formation plus nuclear reactions. But that's very slight compared to what comes in from the sun. We have interactions with the moon, that create tides and so forth. Again, we don't take advantage of that very well. And again, very slight compared to what comes in from the sun. And so what I'm going to do next is talk about power and work from the sun on down, just because there's a lot of confusion about this. What's bigger, what's smaller, and it's kind of interesting. All the problems that were on the stripes of the elephant in the slide a few slides, in order to address those, we're going to need huge changes in the flows of water, carbon, nitrogen, and probably quite a few other elements. These are massive flows of matter and energy. In order to change those, it takes work. Not just a change in technology, not just a change in policy, but work, force times distance. Force against resistance. So this presentation today is in large part about work, okay? Not necessarily species or anything, but about work. Who's going to do the work? Let's start with number one. What comes into the, what the sun produces is a very big number of watts. By the way, a watt, James Watt figured that a brewery horse could lift 180 pounds, 180 feet in 1 minute. In other words, it could pull me out of a 180-foot well in 1 minute. That became a horsepower. Horsepower is a unit of power, which is work per unit of time. We don't need to belabor the abstract stuff here, but I just want to give a couple of contexts to here. And that's, the numbers here aren't super important, but I hope that they give you a context and an anchor for your imagination. What comes in from the top of the atmosphere is over 1,800 horsepower per acre. Those brewery horses would be on top of each other. Okay? And about a third of this is reflected. It does no work. It's reflected off of clouds, dust particles, white hats, reflective surfaces of all kinds like snow and ice. What reaches the surface is about 2/3 of that, about 1,200 horsepower per acre. That reaches the surface. And I'm talking averages now, day and night, all seasons, all latitudes. And we can be very much higher than the average, and we can be very much lower than the average. You've got to watch out for averages. As Fred Provenza likes to say, the average human has one ovary and one testicle, and you hardly ever meet one. So we have tremendous input of solar energy. Of the 1,200 or so horsepower that reaches the surface, about 2/3 of that is absorbed as heat, and it drives currents and winds. And that, of course, is a tremendous power. You know, hurricanes, tornadoes, big supercell storms, all of our ocean currents. This is a beautiful animation that NASA or NOAA made of ocean currents, and it's worth seeing. It actually moves, and it's beautiful. All the little circles and jars, and there's a tremendous amount of flow of matter and energy there. Okay, approximately the other third of what hits the surface of the Earth is what it does. The work it does is it evaporates water. You know, it takes a tremendous amount of energy to move water from the liquid to the vapor stage. And so it evaporates from ocean and lake surfaces, it evaporates from soil surfaces, it evaporates from plant tissues. And that's a tremendous amount of work, 433 horsepower per acre on average. And of course, in a heavy rainstorm, that is channeled, and it can be a very destructive force, as we all know. Moved a tremendous amount of material. Now the carbon cycle, on the other hand, uses only a pinhole's worth of sunlight. Most of the sunlight energy that strikes a green leaf is not captured by photosynthesis. It's reflected, it's absorbed as heat, or it evaporates water. A tiny portion is captured by the process of photosynthesis. And it's around 1 horsepower per acre on average. That includes the oceans and everything else. It includes the deserts, includes Antarctica. A rapidly growing cornfield in late July can probably reach 20 horsepower per acre of its photosynthetic capture. Okay, so this is an average. And what do living organisms do with that energy? Well, it becomes part of the circle of life. And this was known several hundred years ago. The carbon cycle, where plants take up carbon dioxide and use sunlight energy to split water. And then the carbohydrates that they produce are then broken down in all sorts of biological processes and returned to the atmosphere as carbon dioxide. Okay, this is the circle of life. This is literally what makes the, not quite literally, but more or less what makes the world go around. The history of the carbon cycle is kind of fascinating. Without living organisms, we would not have a high oxygen atmosphere. Without that high oxygen atmosphere, we would not have stratospheric ozone. We would probably be a planet pretty much like Mars. And Mars may have had a great deal of water at one time, but without that stratospheric ozone shield, ultraviolet light photodissociates the water molecule, the hydrogen escapes the gravitational pull of Earth. If you lose your hydrogen, you've lost your potential for water. So the work of the carbon cycle of photosynthesis and respiration and that ongoing thing of life, the work of life, is responsible for at least 10% of our surface rocks, the Earth's crust. We're talking about chalk, limestone, calcareous shales of various kinds. It's responsible for the composition of the atmosphere. It's responsible for building soils, for quite a bit of ocean chemistry, and, as I said, for retaining the Earth's water. So there's much of what we regard as the physical environment of Earth has been, in fact, created by life, by the work of life, over eons. And the other part of this cycle is respiration, or burning, or oxidation, similar names, where the carbon compounds are dissociated, yielding energy, and that's what drives every thought in this room, every feeling, every twitch of an eyelash, is the reverse process of photosynthesis, where we eat carbon and we breathe it out. Our cells respire it and we breathe it out. That's how the carbon cycle works through the human body. What do we do with this? Let's go back a little bit. A lot of what is done by respiration, even by bacteria, is in the form of knowing. And we usually associate the word knowing with conscious knowledge. But I would say that the bacteria, the plants, they respond in real time to environmental stimuli, salinity, day length, temperature, all the hundreds of other things. And we may not regard that as knowledge, but it is a form of cognition, recognizing the environment and responding to it, interacting with the environment. I call that knowing. And with humans, for example, we know that we know. We're aware of our own thoughts. The proof of that is that we talk to ourselves. Right. That we use language to describe our experiences, our beliefs, And this may seem a bit abstract, but it's solar energy is what I'm saying. And we'll talk about how it relates to everything else in a minute here. Knowing that we know, and it's a very slight use of solar energy. And if we become aware of how we come about our beliefs, and I think that was a little bit what Steve was talking about this morning, Steve Siemens. If we become aware of how we arrive at our beliefs, how we form our attitudes, that's also a use of solar energy. It's probably quite rare and rarefied. But these are all descendants, direct descendants of the solar energy captured by plants. This is a summary of it. It's probably pretty hard to read in the back of the room. But reflection, surface heat absorption, water cycle, and then the carbon cycle and its descendants. And the majority of sunlight produces climate and other things according to somewhat predictable physical laws, the big stuff up here. But the carbon cycle and its descendants, using only a sliver of sunlight over time, are the most powerful and creative planetary force. Because of what the work of life has done to the environment. And there's a lot of influence coming up through here. I believe that human behavior is changing our climate. And a lot of the things up here, changing the surface heat absorption, changing the water cycle in various areas and regions and so forth. And for sure, changing the reflectivity of the planet in some ways. And I don't require people to share that belief, but what it does for me is it shows that there's tremendous influence upward. And this is because this is not an equilibrium situation. And this is an important concept because it relates to how we can, what power do we have to change things. If you look at a still lake, not a ripple on it, it's in a static equilibrium, if you will. If you want to move that water, say if you're a teenage boy and you want to create waves or something in it, you can do cannonballs in it, you can get an outboard motor or a jet ski and zip around in circles and flap your arms and do a lot of work, essentially. And you can make a lot of waves. But as soon as you stop your work, time will erase it. It'll become still again. It's hard to change something that's bigger than you when the things are in equilibrium. If we take a running stream, fast-moving stream on the other hand, which is not in equilibrium, if you stick a boulder or a log in a certain bend of that stream, you can change things, and time will be on your side. You can be strategic about it. The other example would be for equilibrium versus non-equilibrium. Take a 40-ton truck sitting in the left lane with its engine off. If we want to move that into the right lane, it's going to take a big crane, a couple of giant forklifts maybe or something, because that's just dead weight. We'll have to shift it to the left, to the right lane. But if we're going down the road at 60 miles an hour, all it takes is a slight twitch of the steering wheel to move that truck from one lane to the other because it's no longer in equilibrium. In other words, we're dealing with a sensitive system here. The flow of sunlight through particularly biology. And the lesson I take from that is that creation is now. It's not just in the past, it's now, it's ongoing. The decisions we make are affecting everything, and they have cumulative effects. And one of the things about the carbon cycle is that it is much less powerful than the water cycle, but it influences it tremendously on land, okay? Because with photosynthesis, biomass is created, soil organic matter, litter over the soil, roots, microorganisms, all those things, which slow down the flow of water over soil. Without biomass, our soils would wash into the sea eventually, without plants. These are the main flows of carbon, and notice that fossil fuels aren't in here because they're fairly minor in this big flow here. They're significant, but they're fairly minor. The major flows of carbon on Earth are biological. A very tiny part of that is geological, and a small part of that is burning fossil fuels. Most of it is biological, driven by photosynthesis. Main flows of water over here, and this is driven mostly by solar energy, evaporating water from the surfaces. Water vapor is lighter than air. It rises effortlessly. When it cools, it condenses, falls down with tremendous kinetic energy. But what I would like you to notice here is that for both of these huge cycles, soil is in a key position here, particularly for human welfare. There's a lot of talk about water scarcity too, but the basic fact is that we're not losing water on Earth. It's not going off into space very much. A little bit is, but very little. And it's not leaking into the center of the Earth. It's a cycle, and soil plays a huge role in that, in feeding aquifers, and as well as keeping plants growing. Both of these cycles are intensifying, speeding up. When you have bare ground, we tend to lose soil organic matter, as a lot of the other speakers here have illustrated the mechanics of that. And when we have bare ground, we have tremendous amount more evaporation, and as well as runoff. And there's quite a bit of evidence that globally the water cycle is intensifying, which will probably lead to more droughts, more flooding. The evidence includes satellite evidence that there's more water vapor in the atmosphere on average than there used to be, and that the places where water is evaporating off of the oceans are increasing in salinity, which means there's more evaporation taking place probably. Anyway, so there's quite a bit of evidence that the water cycle is intensifying, speeding up. And to put this in context, on the surface of the Earth, we have trillion watts. Our technology, all of our technology, nuclear, hydropower, wind, solar, everything, mostly fossil fuel based, is powered at about 16 trillion watts, okay? Geologic forces at the Earth's surface, exemplified by volcanoes, earthquakes, the movements of the crustal plates, about 44 trillion watts. And in some places, people use this power. In Iceland and Hawaii and other places, the geothermal power is capturable because it's intensified in certain places. But over the average over the Earth is very slight. The force of life, the work of life, the power of life is about 130 trillion watts just in photosynthesis alone. And its leverage over the water cycle would probably multiply that at least 8 or a dozen times. So it is by far the most powerful and creative planetary force, is the work of life. And I'm talking about diversity of species. There's that contributes all to it, but as a power, it's tremendous. And we don't recognize it particularly those of us who have grown up in cities and urban areas, because this power is spread out, it's gradual, it's quiet, it operates at normal atmospheric temperatures and pressures, and at voltages lower than an AA battery. Photosynthesis happens at about 1.2 volts of electrodynamic potential. Just the opposite of a Cummins diesel. So we typically don't recognize this as power and work, although it's tremendous. Where this all comes together is in the soil aggregate on land. And this is where the carbon cycle, as many of the other speakers here this time around have emphasized, the sticky secretions that hold the mineral particles together and create habitat for all sorts of other microbes. And incredibly importantly, maintain pore space for the absorption and infiltration of water. Without that pore space, you've all probably seen Ray Archuletta's just demonstrations. When there's no pore space, we have tremendous runoff and very little infiltration. This is not a very good picture of a soil aggregate, so I found another one. That's actually a more detailed picture, and that's kind of what it's like. It's like a big city with all sorts of surface areas and activities going on that mostly invisible to us, of course, unless we have a microscope, and even then it's hard to see. But it's a very we have cities underfoot, so to speak. So the upshot of all this is that human decisions can change not only the dimensions of the players, they can change the board itself. Does that make sense? I'm using a bit far-fetched of analogy here. But it's not just a matter of political struggles. You can actually, or fighting over this or that input or this or that species. You actually change the board itself by developing soil. And we don't pay a lot of attention to that. I mean, we do pay attention to yields in agriculture, bushels of corn or wheat or whatever per acre or per inch of rainfall or per dollar of input cost or whatever it is. And those are good, particularly the latter are very good measures. But we tend to be focused, first of all, on species, on practices, on problems, and that's what we map pretty much most of the time. And this is from the National Agricultural Statistics Service. And I think Burlington is right either here or here. I can't quite remember. But this is a fairly tight shot from the 2013 cropscapes layer. The yellow is corn, the dark brown is wheat. I can't remember what this color is. And this is not farmed, pretty much, is their classification for 2013. Okay? You can summon up all the years and find out what species of plants made up crops and so forth, and see rotations and so forth. This is a very usable tool if you want to see what was planted where. But it doesn't really track energy flow or carbon cycling or anything like that. And there are opportunities to do that. There's interesting technology around that has been around in some cases for quite a while. This is a Landsat satellite enhanced vegetation index. This is Burlington right here. And this is just about a year ago, February through March 6th. It's a 32-day composite. And what these colors mean is that the green, there's some photosynthesis going on. The dark brown, almost none. The lighter brown, a slight bit. Okay, and this is well before the big growing season, of course. But you can see there are some green patches around. And since I don't know the country, what are those green patches, you think?
Wheat,
Wheat?
right?
Yeah, winter wheat.
What month did you say it was?
February.
February, March. So it's probably winter wheat. And you see, you know, one pivot with a little bit of that in there. Okay, let's advance to the summer. Pretty much the same scene. And now we see a lot of pivots that are dark green. Still see a lot of land that's not doing too much. Seeing the waterways going through, they're probably, perennial grasses? But this is you know, we're right the maximum input of sunlight here. And still a lot of the land is not doing a whole lot here. And if we go to October 16th through November 17th, pretty much the same scene. We have quite a bit less, of course. And you start to see a lot of pivots that have probably been harvested or dried down, and then maybe wheat in the corners that's still capturing solar energy and converting it into sugars and starches. This is kind of an interesting tool. It's not very citizen usable yet, but it will be. USGS only started making Landsat imagery available to the public in 2008. And now Google, the foundation arm of Google, is making this increasingly available so that people can take a look at it. And what this is a vegetation index. Plants reflect, they absorb a lot of red and blue light, and they reflect a lot of green light, and they also reflect a lot of near infrared. And it's the multispectral aspect that's figured out to approximately measure the intensity of photosynthesis with this. Here's another image from Mexico, and I've sampled soils on this ranch, and this is a huge place. And the west boundary of this ranch is right along there, and that's about a 9-mile boundary. This is a large place here. And the boundary goes about like that. And what you see here is a tremendous difference caused by management. The guy who runs this ranch is a very progressive grazer using planned holistic grazing. And over the years, he's really made a huge difference along this west fence here. And this is a short season shot, only 32 days, August through September, which is about right after when they get their rain down in Sonora, Mexico. But there's a tremendous amount more forage here than here. Tremendous amount more photosynthesis. And this, if we have longer imagery, which we will have pretty soon here, we'll be able to see some real fence line contrast between managers if we can do that 6 to 12 months at a time. If you look down in an airplane and this area is green and that's brown, doesn't mean anything. We know that because you might have just harvested here or whatever, the grazing difference or whatever, just the timing. But if we can composite this, averages over 6 to 12 months, and maybe even get numbers, we'll be able to track photosynthesis which is the input for soil aggregate formation, soil carbon, and so forth. And I like to show this slide to urban people and say, what do you see in terms of energy there? And I took this in Central Oregon, right around the solstice, when we have maximum solar energy. We had excellent soil moisture. And we have a chem-fallow wheat field in the foreground. And people say, yeah, there's a whole bunch of energy being generated in the background. But this is what I call a sunshine spill. And that's the energy that can power our lives, power our communities, power our economies in large part. And that can build soil aggregates. And the soil aggregate is the carbon-rich soil aggregate is in many ways the fundamental infrastructure of our civilization. Because without that soil aggregate, we lose our infrastructures of steel, concrete, and asphalt from erosion, flooding, undermining, blowing dust, whatever. Here's another picture of a sunshine spill. And of course, what are the prospects for people, for the next generation here? They look pretty grim. Prospects for the next generation here are quite a bit different. If we can build those soil aggregates, if we can build diversity and profitability, this farm is profitable. One of the things that we're doing is the Soil Carbon Challenge, which is measurement of soil carbon change, mainly on grazers. And soil carbon is a fundamental attribute of soil aggregates. We realize that these are carbon-rich, sticky glues and cements that hold these soil particles together. And last October, I was remonitoring some plots in southeast Saskatchewan. And these are all on our map, by the way, on our website, soilcarboncoalition.org. These are all mapped. We use open data, which is different than most soil sampling. The soil sampling we do is a different purpose than selling you an amendment or a fertilizer or compost tea or biochar or whatever it is. It's sampling to detect a change in a fundamental property, change over time. And the requirements for that sampling are a little different. I don't just walk the field in a W pattern and scoop up some soil. I actually do a very careful grid pattern with compass and tape, because my GPS isn't one of those $15,000 things. Compass and tape, usually some kind of permanent markers, lines of sight, so I can be within a few inches. Come back and resample core samples on a grid pattern, different grid pattern each time, so we're not putting the probe in the same hole. And here we have a very significant carbon increase. And by the way, 5 out of the 5 farms I resampled up there, and these are grazing operations, increased carbon sometimes by 40 to 60% in 2 or 3 out of 3 layers that we sampled. Sampled from 0 to 10 centimeters 3 years ago and this fall, and got very significant increase. This is total carbon, by the way. We're talking at whatever 60%. This would be like 14 to 16% organic matter in the top 10 centimeters and the top 4 inches. And a huge relative increase in the next layer, 10 to 25 centimeters, that's like 4 to 10 inches. And pretty insignificant down here. But again, this is 3 years. And actually a decrease, but I don't even regard that as, that's within the limits of measurement here. But this is our soil carbon challenge, mainly on grazers. And what it gives them is a sense of possibility and the recognition that they're on the right track. And in some cases, these are fairly low diversity grasslands. In every case, this has once been farmed, been put back to grass. Mostly smooth brome, some bluegrass, and a lot of vetch coming in, sometimes clovers, but not a lot of diversity there. But they use fairly high stock density, are very careful with their timing. A lot of people talk about payments for ecosystem services and carbon credits and that sort of thing. And I think those things may be coming, but I don't think it's quite the same as a lot of people predict. And the example I want to give you is from a city. When I travel the country, I sometimes travel in a converted school bus doing soil sampling. The number one issue is water, always. The reason we measure carbon is it's in some ways simpler to measure than measuring water. Simpler and more accurate. And it has a direct relationship. The number one issue is water, and the city of Charlottesville, Virginia, needed improvements to their stormwater system. And they went around and around, where were we going to get the money to do this? And they decided that because of the availability of aerial photography and things, they were going to assess property owners within the city of Charlottesville a fee depending on the square footage of impervious surfaces. So you can go onto the City of Charlottesville website, go to their ArcGIS viewer, zoom in on a property, and you'll get this kind of result. This is the parsonage for Ebenezer Baptist Church, and it has 3,136 square feet of impervious surface on it. And so they get assessed a stormwater utility fee of over $100 based upon that square footage of impervious surfaces. The reason I'm bringing this up is because it's easier for governments, municipal utilities, water utilities to require you to give them money than it is for them to give you money. That's the typical way of governments. Governments tax easier than they give out. And this is to cover the costs of an infrastructure improvement. And basically, people can't argue with this. The measurement technology is there. It's not very expensive. They don't have to send an inspector out with a tape measure to measure the roof. They can do that with aerial photography. Or the asphalt driveway. If you rip up your asphalt driveway and put in porous pavement, or if you put in some sort of bioswale or something, you can go to the city and ask for some form of relief, and they chances are they can give it to you. But I think this is the future of exchanges between urban and rural areas on the basis of water, for example, because we can actually measure impervious surfaces. And in general, I see a shift from the power of technology to the power and work of life, which globally is 8 or 9 times what our technology can do. And I think that's going to be very important for leadership. One of the purposes of our Soil Carbon Challenge is to shift the leadership, as it were, from the talkers to the doers, to recognize people who are actually building growing soil based upon measurements, not on rhetoric. And the final slide, I think in terms of soil carbon and ecosystem function, I think this is where we are today. We have a little bit of data. Most of it's hidden. It's not accessible to the public. It's buried in research papers or behind subscription paywalls, or is not in an intelligible format in terms of biological work. And we have all sorts of predictions, fears, and advocacy trying to influence things. Whatever policy we come up with is very unstable. Lots of different opinions, lots of backlash. One of the things we're trying to do is to move toward this more stable structure when we have more data on outstanding innovators capturing more sunlight energy. And with that, we can build a sense of possibility and management capacity and effectiveness at every scale, from the 40 acres to the nation as a whole, because we are making decisions based upon what we think is possible. If we think it's impossible, we won't try it. And as Steve said this morning, the difference, let's concentrate not on the fictions of change, but on the facts of change. And that's what we're trying to do with our Soil Carbon Challenge, which, by the way, is going to expand to, we'd like to work with conservation districts, communities, farmers, to collect data about biological work. Biological work, I mean the work of life. And there are a number of different indicators besides soil carbon change, which I think is a great one. There are water infiltration, very easy to measure. It takes a little bit of time to wait for the water to sink down in those rings sometimes, but it's a good time. You can do a lot of other observations while you're waiting for that water to settle. And in some cases it might go very quickly. I'm talking about the NRCS advocated infiltration ring. And I pack 5 of them, by the way, and I run 5 concurrently to do, because if it's going to take 30 minutes, I don't have to wait 3 hours. And there are also economic measures. For example, in the 1990s, I visited a ranch in South Africa where the rancher was told by the extension agent, he said, the amount of beef you can raise on this ranch depends on the amount of rainfall you get. So Sandy Speedy, being a guy of character, he put out rain gauges, and he knew how many pounds of beef he each year. And he was in the process of implementing a pretty tight grazing plan, and was, over the next few years, he got a lot of his bare ground covered up with growing grass. The rainfall was trending downward during that period. And over 15 years, he tripled the pounds of beef per inch of rainfall he produced. And he said, no, it's not management. I mean, it's not rainfall, it's management. In other words, he showed the lack of correlation between rainfall and yield on his beef. Okay? And I think an issue we have in the United States and with agriculture too is that we tend to think that we can't do things, or we can't change the board on which the game is played. But if you change the board on which the game is played, there's a lot more possibilities, and we do have agency. There's a lot of speakers here this week that delve into the mechanics of building soil carbon and adding biology to mineral soil and so forth. And I'm not trying to steal their thunder. It's a lot of good stuff. But the important thing is it's a human issue, and it's one of possibility. We need to recognize that possibility. We can recognize it. If we can recognize it, we can imagine it. Same kind of thing that Steve was talking about this morning. Recognize it, we can imagine it, and we can work in alignment with that huge power and work rather than just merely against it. And that can result in huge savings, because this savings of all kinds of things. Most of you are probably familiar with Gabe Brown, who's a stunning example of this, who doesn't use nitrogen fertilizer and gets yields comparable to his neighbors and so forth, by capturing more sunlight energy in the form of photosynthetic capture, and also water captured in soil pores, which is a form of sunlight energy as well. In fact, water captured in soil pores is probably, on land, it's probably the most significant form of sunlight energy that we can capture. And it's mediated by biology. That those plant exudates feeding the microbes that can then build those sticky glues and cements that hold the soil aggregates together. And when the rain comes, then it can be accepted and held by those pores in capillary tension. And that's the principal capture of sunlight energy by living beings is soil water, soil moisture. And it's huge. Anyway, that's about all I have for today. I'd be happy to talk questions or statements. Anybody would like to share what their observations or learnings are? Be happy to hear it. Or questions.
So you showed that, you know, the difference between the power of life versus all the others and how much more it was, but just because you couldn't see it, you know, it was fairly low level. How do you get that, translate that to the average person, consumer, city person, whatever, you know, to understand that, because they see the windmill or, you know, all that, you know, how do you get that message across to them?
I think that's a great question, and one that I've been stewing about for quite a while. And I think one of the solutions is, one of the potential solutions is mapping. If we can map that power of sunlight. And you know, if you look at Earth engine photosynthesis, Landsat photosynthesis shots of Iowa, for example, it's very green in July and August, but almost all the rest, from the tail end of the growing season around, it's not that different from a desert in terms of its photosynthetic activity. And I think that's, when we get that citizen usable, which should be within the year, that will be, I think, a powerful way to show, to map sunshine spills. And, well, this is a sunshine spill, but here's a green square or center pivot here, what's going on? Center pivot's irrigated, but here's a green square here of dry land. Right. What's this person doing differently? That's a possibility that may illuminate the rest of this.
So like in grazing, you know, like Jim Gary's talked about, you know, leaf area index. I mean, you could actually use that. That's what you're talking about. Yeah. On a large scale, is what's the leaf area index of that particular, and that's going to tell you how much energy you're capturing.
Right, right. Yeah, and these satellites go over every 8 or 16 days, you know, so it's not like, I mean, you can add to that with, say, drones or something, if they have multispectral capabilities. But change over time, you know, these satellites go back to 1984 and potentially further back, so we can get that imagery. And what I think it would, it's one thing to criticize people, but to show what's possible is a whole different